Okay, so I have cleaned up all of my highlighting on slide 4 so that we can see how the 4 named type conversions relate to the 4 examples of using C-style typecasts that we looked at on slide 4. Constcast, shown here on slide 6, is only able to alter the constness of an expression. That is, it can add constness to an expression that is not const, or much more commonly, it can take away constness from an expression that is const. So using constcast here on P accomplishes the same thing that we did over here on slide 4 using an ordinary C-style cast. That is, P is a pointer to a char const, and what we're using constcast to say is take P and treat that as a pointer to char. So we've eliminated the constness from P, or technically from the thing that P points to. The way you use constcast is to give the data type that you want to convert to in a pair of angle brackets, and then the expression that you're trying to convert is put in parentheses following the angle brackets. So constcast, open angle bracket, char star, close angle bracket, and then paren P is how you indicate that you want to take P and convert that to a pointer to char. Now, adding or eliminating constness is the only thing that constcast is allowed to do. It's more restricted than a C-style cast, which can do anything. For example, if you attempted to use constcast, as we're doing here on the bottom of slide 6, to convert P into a pointer to int, this would give you a compile time error, because not only are you eliminating const there, but you're actually attempting to change the data type of P's value as well, and that's not allowed. So the named casts are more tightly focused and hopefully makes more clear to the developer and makes it safer in the compiler to narrow the kinds of casts that you're doing. Next, we're going to take a look at static cast. Static cast can be used to convert pointers to and from void pointers, and also can be used to do numerical conversions, such as double to int or int to double, and so forth. Here I'm taking I, which is an int, and I'm converting the address of I, whose data type would be pointer int, into a pointer to void, using my static cast. So static cast here is taking an int pointer and converting it into a void pointer, which I can then successfully store in this void pointer variable PV. In the next static cast, I'm taking PV and I'm converting that into a pointer to unsigned char using static cast. So this is the same address. It is originally the address of an int. I've converted that to a pointer to void, and then I've converted that into a pointer to an unsigned char. Why would we ever do such a thing? Well, an int is, on our systems, 4 bytes long, and there are 2 different styles of organization of bytes in an int on different processors. One style is what's called little endian, which stores the low order byte in the first address up to successively higher order bytes. And the other style is what's called big endian, which stores the big order byte first down to the low order byte last. And so what we might be interested in doing here is determining whether the 127 that I contains is stored in the first byte at that address or stored in a later byte in that address. Okay, so if 127 is stored in the first byte at that address, that implies that we're working on a little endian processor as opposed to a big endian processor. Now, you can use static cast to convert to and from pointers to void, but you can't use static cast to convert directly from one specific pointer type to another specific pointer type other than void. Here, if I try to take the address of an int and convert that to a char pointer, the compiler will complain at me. So static cast does allow me to convert from one kind of pointer to another, but it requires me to be careful and thoughtful about how I do this. Static cast can also be used to convert among numerical types. So static cast could be used in the way that we're doing over here with double on slide 4. It would allow us to take an int value and convert it to a double, or a double value and convert it to an int, and so forth. Reinterpret cast, shown here on slide 8, is the one that allows us to handle all bets are off conversions from non-pointers to pointers and vice versa. It's the one that will allow us to take an integer value representing the address of something in memory and convert that into a pointer. So here we're doing essentially the same thing as we did over in our second example on slide 4, but using the more carefully checked named cast as opposed to the C-style cast. Dynamic cast handles conversions of base class pointers to derived class pointers. That is, dynamic cast allows us to do the kind of thing we did here on the bottom of slide 4, take a base class pointer and convert that into a derived class pointer. But dynamic cast will only do that if the base class pointer really is pointing at a derived class object. So of the 4 named type conversions, const cast, static cast, reinterpret cast, and dynamic cast is really a new feature that we didn't have using the old-fashioned C-style casts. And we'll have a lot more to say about that later. It's also possible, as shown here on slide 9, to use curly braces to do type conversions. This is sort of a function-like type conversion. That is, we give a type name like double and then some expression in curly braces. This typecast will only be permitted if the conversion is what's called a non-narrowing conversion. That is, it's fine to convert from an int to a double because all int values are guaranteed to fit in a double object. But if you attempt to go in a narrowing direction, that is, if you attempt to convert from the double 3.4 to an int, well, an int would chop off the fraction part. This is what's called a narrowing conversion. And so you'll actually get an error from the compiler if you attempt to do a conversion in this way. So in other words, the curly braces can be used to perform guaranteed value-preserving conversions. That is, from little types up to bigger types, not from bigger types down to little types. In this final example, you might argue, well, 5 stored in an int can fit into a char perfectly fine, but the curly brace type conversion does not consider the current value of j. It just considers the type of j, and since j is an int, and there are many values of int that won't fit into a char, if I attempt to convert j's value into a char, the compiler will give me an error. So the various forms of casts and curly brace construction are explicit type conversions that the programmer specifies that they want to do. There are also, of course, implicit type conversions that the compiler does for you. And, of course, we've seen this in things like this arithmetic expression in which we have a double, 2 ints, a bool, and a char. This thing is going to be evaluated from left to right within precedence levels. So the division actually has the highest precedence. And so very likely this is an error on our part. 7 divided by 3 is going to be exactly 2, the int 2. And only then, after that division is finished, will the 2 that results be converted to a double so that we end up with 12.5 plus 2 is 14.5. Then we subtract 1.0, which is what happens when we convert true to a double. And then we add 49.0, which is the ASCII value of the character 1 converted to a double. All right, so this expression here compiles and runs just fine. We may be surprised by the result if we weren't aware that we were going to get an integer division here before the addition and subtractions occur. But the compiler simply does this for us and doesn't display any complaints or warnings.